Good morning, everyone. I am Kajasit Tolek from Software Design and Asset Laboratory. Today, I will present my doctoral dissertation entitled An Infrastructure for Collaborative Machine Learning on Resource-Constrained Heterogeneous Environment. First of all, I will introduce you what is the collaborative machine learning. Collaborative machine learning is development of machine learning model collaboratively by sharing datasets and models among the machine learning model developer. For example, in this use case scenario, there are three hospitals, A, B, and C, where we would like to develop the machine learning model to identify the COVID-19 from chest X-ray images. In the traditional process, hospital A and B have to share their local dataset to a centralized server. And then the server have a service to train the model over the local datasets from hospital A and B. Afterward, the other hospital, in this example is hospital C, can download the trained model to influence or continue training with the local dataset on the local environment. But you can notice from this diagram that the client have to expose their local data to a centralized server. So that means this process will make the data loss privacy prevention. So there is another approach to preserve the data privacy for collaborative machine learning, which is called federated learning. Federated learning is a machine learning technique that trains the model across the multiple machines without exchanging the local datasets. Federated learning has been introduced by Google in 2016. In federated learning, we divide the machine learning model on server and client, a global model and local model respectively. At the first step, we deploy the initial global model on the server side, and after that, each client downloads the model from the server to train with the local dataset on their local environment. And after local training, the trained local model is transferred to the server for aggregation in the federated learning algorithm. Federated learning algorithm is an important mechanism in the federated learning to update the existing global model on the server side with aggregation of the local model, such as the fedAVG. So after we update the global model on the server side, then other clients can download the global model to use it with their local datasets. But you can see from this diagram that you cannot see any raw datasets exchanging between the server and the client. For this reason, that's why federated learning is able to preserve data privacy for collaborative machine learning. But in the real-world situation, not all clients can support the same machine learning due to the limitation in the storage capacity, available computing resource, and network bandwidth. Therefore, the federated learning on heterogeneous environment is still challenging. From the problem statement about the federated learning on heterogeneous environment, so I aim to build an infrastructure that enables the collaborative development of machine learning model on heterogeneous environment while preserving the data privacy, which is called the LiberatAI infrastructure. The LiberatAI infrastructure is similar to GitHub and DockHub that allow collaborative development of source code and container images. In the LiberatAI has a model repository to store the model because LiberatAI store the model instead of the datasets. So that means we don't have any data repository in the LiberatAI. For instance, there are two users that would like to use the LiberatAI. Each client has a different existing hardware resource. Each client has their own local datasets. For example, client A and client B will train the model on their local dataset with their local environment. And after that, they upload or commit the model to the LiberatAI. And other client can do the request to the LiberatAI and pull the aggregated model to use with the local datasets. This is the briefly overview of the LiberatAI infrastructure work that I proposed in this dissertation. So that you can see that we're moving the training process from the server side to the client side. So that means the limitation of each heterogeneous environment has to be considered when we need to train or influence the machine learning model on client hardware resource. So in this dissertation, we consider the hardware heterogeneity in three aspects. The first aspect is the heterogeneity of the storage resource. Each client has a different storage capacity constraint. Someone is smaller one and someone is other larger storage. Storage capacity is directly related to the portability of the storage. The variety of the storage resource has an impact to the size of the machine learning model which are stored on those resources. And the second one is a heterogeneity of the computing resource, that normally every machine should have the CPU, but they are different in the specification of the computing power. So some clients might have the computing accelerator, such as the GPU and TPU. The diversity of the computing resource has an impact to the complexity of the machine learning model which are trained on those resources. And the last one is about the heterogeneity of the network resource. Not every client has a machine which are able to connect to the wide network. Usually the wide network can provide a more stable and higher bandwidth network than the wireless network. The heterogeneity of the network resource had an impact to the amount of transfer data to train the machine learning model with the federated learning approach. Therefore, I propose the LiberatAI infrastructure that contains three main components that is able to address tackle the technical challenge for training or influencing the machine learning model on heterogeneous storage, computing, and network resource efficiently. First, I propose the component, which is the model compressor component. It is used to compress the model to fit in the heterogeneous storage capacity constraint. And the second one is a model aggregator component. It is used to aggregate the model from heterogeneous computing resource. And the third one is a model specifier component. It's used to reduce the communication cost for exchanging the model on the heterogeneous network resource. I will explain each model in more detail in each chapter, and I have the last chapter to explain how I integrate those three components to build a LiberatAI infrastructure. So let's start with the first component about the model compressor for training the model with heterogeneous storage resource. The model compressor is proposed to reduce the size of original model while maintaining the accuracy of original model. The proposed method in the model compressor consists of three main steps. The first one is the compression. It's used for reducing the model size, and we have the retaining step to recover the model accuracy while keeping the same size of the compressed model. And after that, I use the model size and model accuracy after retaining to be the parameter for the optimization process. Lastly, I apply the optimization method to find the optimal configuration to compress the model. In this study, in the optimization process, I utilize the multi-objective optimization, which has two main objectives. The first one is to minimize the model size, and the second one is to maximize the model accuracy. So let's start about the model compression technique. The model compression is a method to reduce the size of the model, but it also degrades the accuracy of the model since it reduces the precision of the weight in the model. Due to my literature review, that I show you the table of the comparison of the model compression technique. There are four main model compression techniques. The first one is transfer compact convolutional filter. The second one is the knowledge distillation. The third one is the low rank factorization, and the last one is the parameter pruning and shelling. For the parameter pruning and shelling and low rank factorization can support training from both pre-trained and scratch model, while the transfer compact filter and knowledge distillation can only support training model from the scratch. The main difference between the parameter pruning and low-rank factorization is the impact on the model accuracy. For this reason, I forgot to use the parameter pruning and shelling since we aim to deploy the P10 model on the resource-limited edge device. So I use the vector quantization. Vector quantization is a widely adopted method based on the parameter shelling and pruning approach. Vector quantization is one of the quantization methods which outperform other quantization approach in compressing fully connected layers, which are known to be the most storage demanding layer in the neural network model. So the figure on this slide shows an example of data distribution for parameter value in the machine learning model. For this example, I decided to separate it into the four clusters. First, I have to calculate the cluster, and then I calculate the centroid for each cluster. So now I can reduce the number of parameters to store from the left figure to the right figure. The value in each cluster is represented using the dash centroid, and each neural network model has a different number and distribution of parameters in each layer. Therefore, the different number of centroids must be chosen for each individual layer. I quantize each layer separately and balance between the reduced model size and the accuracy loss to find the best number of centroids for each layer. to be the checkpoint after the quantization process. The size of original model will be reduced, but it also degrades the model accuracy. So I applied the retraining process to recover the model accuracy while keeping the same original model size. So the retraining necessary method to recover the accuracy of the compressed model. The most existing retraining method requires the original label dataset to retrain the compressed model. The original label dataset cannot be accessed because of the privacy policy and license limitation. And using the unlabeled dataset for retraining is highly useful when the original label dataset is unavailable. So I propose the method to retaining the quantized model with the unlabeled datasets. So the unlabeled dataset is used to train the original model and quantized model. In the quantized model, I separate the layer into trainable layer and non-trainable layer. After quantization, some layer will be quantized, so I will keep those quantized layer as a non-trainable layer. Because if we retain or train the quantized layer, the number of parameters will be increased again. So that's why I will keep the quantized layer as non-trainable layer. And after we train the quantized model and original model, we will get the output vector. And after that, we will take the difference between the output vector and the loss and use it to be the teacher signal to adjust the weight in the quantized model. So after quantization and retaining, the model have to pass through the optimization process to find the optimal configuration. So this slide indicates an example of quantization configuration of the LineAI 5. LineAI 5 have 3 convolutional layers and 2 fully connected layers. For example, in the model compressor, perform finding configuration, which is the centroid to control each layer. For instance, the model compressor got the result that we have to use the 280x centroid to quantize the first fully connected layer, and we have to use the 256 centroid to quantize the second fully connected layer. So consequently, after the compression, the size of first fully connected layer is reduced to 2.4, and the size of the second fully connected layer is reduced to 39.11. As a result, the size of the LineAI 5 is reduced to 39.92% with the model compressor component, which is the 1.12% loss in accuracy. So for the optimization, finding the optimal configuration for quantizing the model can be thought as a multi-objective optimization problem because a configuration that maximizes the model accuracy and minimizes the model size at the same time need to be found. To recap, what is the configuration? Configuration specifies which layer of the model should be quantized and the number of centroids that each layer should be used. In this chapter, I apply the NSGA tool as a multi-objective optimization algorithm. NSGA tool or non-dominant sorting genetic algorithm tool, which is a genetic algorithm. I use it because there are 3 distinctive features of NSGA tool. First, it's used as iterate principle, where iterate are given an opportunity to be carried out to the next generation. The second one, it is apply the counting distance, which is explicit diversity preserving mechanism. And the last one, it is emphasized on the non-dominant solution. The optimization for the model compression should focus on the non-dominant solution, since the smaller model might have the possibility to have the higher model accuracy than the larger one. So the figure on the slide shows the first generation when I apply an SGA2 to find the optimal configuration for compressing the LineAI 5, and then I apply the SGA2 until the conversion. In this study, I define the conversion. Generation is occurred when the Pareto fund had not changed for 5 generations. Therefore, I got the optimal configuration on the orange line or on the Pareto fund line. And so the proposed method it has to be evaluated using the state-of-the-art machine learning model for the classification, ligation, and semantic similarity tasks. After I applied those models to the model compressor, we got the compressed model. I evaluate the compressed model into 2 aspects. The first one is the model size, and the second one is the model accuracy. So I will investigate the model size and accuracy during optimization for the LineAI 5. Let's start with the model size. At the beginning, the optimization, the model size grows rapidly and reach the plateau to 5 to 10 generation in the board. And in contrast, the decrease in model size was relatively slow during the optimization. And for the model accuracy, the model accuracy converged very quickly at the beginning of optimization, and then accuracy only slightly increased. So this figure on the slide shows the Pareto font from our proposed method to compressing the linear 5, and the proposed method is able to reduce the linear 5 size by 39.92% with a 1.12% loss of accuracy. And I also investigate the Pareto font from our proposed method for alter model architecture. As a result, the proposed method reduced the size of the model at least 30% while maintaining around 1% loss of accuracy. And next, I compared our proposed method to 3 existing automated quantization methods like AMC, LilyQ, and AutoQ. So that you can see, obviously, our proposed method provides more than one configuration, but other existing method provide only one optimal configuration. So the result when I compare the proposed method with the AMC, the accuracy loss difference of the proposed method and AMC is just I got the higher accuracy loss than the AMC by 0.06, but the compression ratio from our proposed method is more than AMC, around 23%. And also when we look into the comparison of the proposed method to LilyQ and AutoQ, our proposed method that is able to maintain the accuracy loss higher than the LilyQ and AutoQ by 18% and 25% when compared to LilyQ and AutoQ respectively. And also the compression ratio, our proposed method is reduced less than the LilyQ and AutoQ by 1% and 5% respectively. To conclude this chapter, I propose a method to automatically find the optimal configuration for quantization and retaining machine learning model without labeled datasets. And an SGA2 multi-objective optimization is used to automatically find the optimal configuration for quantization that simultaneously minimize the size and maximize the accuracy of the model. The proposed method was evaluated using the state-of-the-art neural network model for classification, regression, and semantic similarity tasks. As a result, the proposed method reduced the size of the model at least 30% while maintaining less than the 1% loss of accuracy. For this chapter, I published one journal article and one international conference paper. Let's go to the next chapter about the training model with heterogeneous computing resource that I propose the model aggregator. The model aggregator is proposed to aggregating the model with heterogeneous structure from the diverse computing resource because since the existing federated learning algorithm allow only the model with homogeneous structure to be aggregated. In practical situation, not all edge device can support the same model due to the limitation in the available computing resource. So I propose the method in the model aggregator that enables federated learning to combine the neural network model with heterogeneous structure. First, I apply the FED AVG of federated averaging, which is used to update the global model using the updated parameter from the local model, which has a homogeneous structure. After we update the model for each model structure, which has homogeneous structure, we apply the weight average ensemble to combine the model which had heterogeneous structure, and now we got the ensemble model. And next, what is the weight average ensemble? Weight average ensemble is a simple and efficient ensembling method to combine the model with heterogeneous structure. I use this equation to evaluate the weight for each output card of each model architecture. I divide y is equal to the final output vector, x be the input, n be the number of the model architecture, I be the prediction of x using I model, and the alpha I be the weight vector for the I model. And alpha I is have to be determined by applying the optimization algorithm. So in this study, I applied 6 backblock optimization algorithms to determine the alpha I. So that's all for the proposed method. And I have to evaluate the proposed method in model calculator. I use the cipher10 datasets which contain 70,000 images for 10 output class. So I separate into server-side data and client-side data. For the server-side data, it's 10,000 images for tuning in the weight, average, and sampling process, and 10,000 images for validation to evaluate the accuracy of the model. And for the client side, we deploy the training dataset, which consists of 48,000 images for training. By each client had 40 images. So I widely use the classification machine learning model, which have the different required number of floating point operation, which require the different specification of computing power. In this evaluation, each model architecture is simulated to distribute over 300 clients, and each model architecture is calculated with a fed AVG for homogeneous structure first, and then applied to the weight, average, and sampling, and now we got the sampling model. In this evaluation, I investigate the model accuracy for each optimization during the weight and sampling, and compare the model accuracy before and after sampling. So let's start the model accuracy for each optimization. Before optimizing the weight, each model architecture had the same weight. Then the accuracy is around 74%, and after optimization, TPE is able to achieve the highest accuracy by increasing the accuracy from before optimization by 14.5%. And this slide will show you the example of the optimized weight for the output card of each model architecture when we apply the TPE to determine the weight for each model architecture. So for the same output class, model with a darker cell are weight heavier than the model with a lighter cell. So taking the X output card as an example, MobileNet had the highest weight, while the DenseNet 169 had the lowest weight. So this suggests that the MobileNet is able to identify A class more accurately than the DenseNet 169. In this manner, the model that achieve the higher accuracy on the particular class will have the higher weight assigned to them after the weight optimization. And next, the model accuracy before and after sampling. So before sampling, each model is distributed over the 300 clients so that the result of the before sampling is occurred from the model that trained over the data from the 300 clients. And for the after sampling, I assembling every model architecture so that the result of the after sampling is the accuracy of the model that trained over the data from the 1,200 clients. As a result, the proposed model is able to achieve the model accuracy higher than the VGG16 by 4.29%. So to conclude this chapter, I propose the method for combining a neural network model with heterogeneous structure. I propose the method to utilize the weight, average, and sampling to combine the output class from the different model architecture. The backblock optimization is used to tune the weight for the output class of each model architecture. I compared 6 backblock optimization algorithms. I found out that TPE was able to achieve the highest model accuracy. So for this chapter, I published one international conference paper. So let's go to the next chapter about the training the model with heterogeneous network resource. The objective of the model specifier which is the training the model with heterogeneous network resource is reducing the communication cost for exchanging the model on heterogeneous environment, because when we have to deploy the original model on the client side and server side, we have to exchange the both model into client and server. So we have to reduce the communication cost for exchanging the model, because the existing federated learning algorithm requires the whole dense model for exchanging the model between the server and the client. So I will present the proposed method for the model specifier is separated into uplink direction and downlink direction. I will explain in the uplink first. So when we have the global model in the server, the global model will be distributed to every client, and every client will have their own local dataset, and then we perform the local training. On the client side, we have to do the local model specification, which use the local model before and after the local training to construct the Spark local model. And after that, the Spark local model will return to the server to construct the global model for the calculation to be the update, the existing global model. And next, we will use the global model to distribute it for the client on the downlink direction. The global model also has to do the global model specification, which is use the specification pattern of the Spark local model to construct the Spark global model, and then Spark global model will distribute it to every client. Actually, the process in the client A and client B will occur in the same process, but due to the space limitation in this slide, I will show you what happened in the client A. When the Spark global model returns to the client, the Spark global model has to update the local model. And then the local model we use to continue the local training. We repeat the same process in the previous slide. So that you can see the overall or overview of the proposed method in this slide, that on the uplink direction and downlink direction. There are three main steps that I need to explain you in more detail. The first one is the local model specification. The second one is the model update. And the third one is the global model specification. So let's start about the model update. Model update is a method to update a dense model using a Spark update sent from the server to the client. For example, if you have the original dense model like shown in this slide and the Spark model like shown in this slide. So in the Spark model, if the position in the Spark model had the parameter value, so that means you have to evaluate those parameter value with the same position of the parameter value in the original dense model. But if in the Spark model don't have any parameter value, so that means you can replace the parameter value in the same position from the original dense model. So now you can get the updated dense model. And next we go to the local model specification. It is the method to extract the most updated parameter to construct the Spark local model. The local model specification is occurred on current slide. It will use the local model before and after local training. So after we have the parameter of local model before and after local training, we have to take an absolute difference of every parameter of the model. And in the local model specification has a Q parameter, which is supplied by the user to adjust the communication cost and model accuracy. For example, in this scenario, we set Q to equal 0.7, which is mean the top 30% of the most updated parameter are selected to transfer. So that means you have to calculate 0.7 quantile of the absolute different value of every parameter. So in this example, we got the value equal to 3.56. So that means we have to select the position that have the parameter updated more than 3.56. So after that, we got the position, we can do the masking on the local model after local training parameter. And now we got the Spark local model that prepared for transferring it to the server side. And then we go to the global model specification. It's a method to use the local mask to construct the Spark global model because the parameter in the mask are still not converged yet at the client side, and then those parameters have to be updated to converge. So for example, we have the Spark local model and global model like shown in this slide. So this process is quite simple, that you know the specification pattern, so that means you can easily to extract the specification pattern that which parameter should be kept and which parameter should be eliminated. So now you can do the masking with the global model with the specification pattern of the Spark local model. So now you got the Spark global model to be transferred to the client. And to evaluate the proposed method in the model specifier, I measure the communication cost for exchanging the model. And we measure the accuracy of the global model on server side. And although the large model can generally achieve the higher accuracy than a small model, but not all edge device can exchange the large model due to the limited network resource. Therefore, the proposed method evaluate using the model with a different scale, and also evaluate on the widely used popular image classification dataset. And this table on the experimental setup that show the configuration that I use in this evaluation. The number of communication route is equal to 10, the number of client in this experiment is equal to 10, and the number of local report is equal to 5, and I use 8 local batch site. So as a result, compare the proposed method to the existing method. So this figure shows the relative communication cost and global model accuracy for VG16 model on the Cypher10 dataset. So the result indicate that the proposed method outperformed than the existing method in terms of the both communication cost and the accuracy of the global model. But there are some existing methods that has outperformed in some conditions, including FedPSO and FedMD, like showing the orange color and green color respectively. I also evaluate the proposed method for the difference model. The reduction of communication cost from FedPSO, FedMD, low-rank approximation, random mass, and quantization are almost identical for all model architecture. But the reduction of communication cost for FedAVG and proposed method are varied to the size of each model architecture. By the reduced communication cost of large model is larger than smaller model. So we investigate why the reason why the larger model are amenable to compression. The figure on this slide visualizes the frequency of updated value per communication route and per client for each model architecture. I found out that the frequency of the small model updated parameter in the large model is higher than in the smaller model, and the larger model receives more low impact updated than a small model. So that means the proposed method is able to adopt those low impact updated in the large model without significant accuracy loss. And to conclude this chapter, I propose a novel method to reduce the communication cost for federated learning by specifying local and global model on the both uplink and downlink communication. The proposed method utilizes exchanging the most updated parameter of the neural network model. The diverse model and datasets are used to evaluate the proposed method in terms of model accuracy and communication cost. The proposed method achieved a reduction in communication cost approximately 90%. For this chapter about the model specifier, I published one international conference paper. So let's go to the last chapter about the LiberatAI infrastructure. That I show how to integrate the three components to build a LiberatAI infrastructure. For the LiberatAI infrastructure, I integrate my three proposed components that I mentioned to you previously to build a LiberatAI infrastructure to handle training the machine learning model on heterogeneous storage, computing, and network resource. So the LiberatAI was evaluated with an application of COVID-19 detection from chest X-ray images. So my experimental result, we have the three main sections. The first section is about the result for the one heterogeneous resource. The second one is the result for the two heterogeneous resources. And the third one is the result for the three heterogeneous resources. And due to the time limitation, I think I will show you only result for the 1 and 3 heterogeneous resources. So this slide will present you the workflow of LiberatAI, which contains my three proposed components and how it works together in the LiberatAI infrastructure. So let's start with the client. We'll select the model in the model repository on the LiberatAI server side, and the model will pass to the model compressor to compress the model to be fit in the client storage capacity, and then the user will turn the model over that local dataset, and the local dataset will transfer via the model specifier to reduce the communication cost for the heterogeneous network resource. And then we will use the model aggregator to aggregate the model that from the diverse computing resource. And now we store the aggregated global model on the model repository. And next, I will evaluate the proposed method with the COVID-19 detection application, which is a typical privacy-sensitive use case for machine learning application. I use the 5 value use image classification model in this evaluation. So one of them is the COVID-net, which is the state-of-the-art machine learning model to detect the COVID-19 from chest X-ray images. The COVID-X dataset is used to evaluate the LiberatAI infrastructure. The COVID-X dataset is the largest open dataset for detecting COVID-19 from chest X-ray images. So let's go to the first result for the heterogeneity of the storage resource. The figure on the slide presents the Pareto fund For the machine learning model, I select the smallest model to calculate the compression ratio from the model compressor component when the loss of accuracy is less than 1%. I found out that the proposed method in the model compressor component reduced the model size of the coordinate less than 152, less than 101, denseness 201, and mobileness at least 30%, at least around 30%, and also investigate runtime for compressing the different model architecture. As a result, the larger model have to take a longer time to compress the model than the smaller model due to the complexity and the size. And the second one about the result for heterogeneity of the computing resource. For experimental setup, I deploy each model architecture to 20 clients so that the total number of the clients is 100 clients. The figure it indicates that the ensemble model produces a higher accuracy than the homogeneous federated learning of CovidNet since the fifth communication round. And next, the result for the heterogeneity of network resource. Since I focus on the limitation of the network resource, I only select the largest model of CovidNet to observe the loss of model accuracy and communication cost. In this evaluation, CovidNet is distributed over the 100 clients. So the result from this figure indicates that the communication cost with specifier component is able to maintain the higher accuracy and lower communication cost than communication without specification. So lastly, heterogeneity of storage, computing, and network resource at the same time. I set up the total number of the client to 100 clients, so that each model architecture have to be deployed on 20 clients. I define two storage capacity constraints, which are 200 MB and 400 MB. For model compressor component, only CovidNet and less than 152 have to be compressed with the model compressor, and less than 101, less than 201, and mobilenet don't have to be compressed, since the original model size is smaller than 200. After we compressed and distributed the model like the following in the configuration in the table, then I start executing the federated learning. I apply the model specifier. The result indicated that with the model specifier produce the higher model accuracy with the less communication cost than the without model specifier. And then I apply the model aggregator. As a result, indicated that with the model aggregator can enhance the model accuracy to produce a higher model accuracy than without model aggregator. To conclude this chapter, I propose the LiberatAI in infrastructure for collaboratively developing machine learning models that allow researchers to work together and potentially build a better model. Federated learning is applied to train the model while preserving the data privacy. LiberatAI was evaluated using the state-of-the-art neural network model to detect the COVID-19. LiberatAI produced a higher model accuracy and utilized the less communication cost than without using LiberatAI. LiberatAI will publish as an open source software and available for international and domestic research community. So this chapter, I have already submitted manuscript to the Future Generation Computer System Journal. And lastly, to conclude this dissertation, clearly there are no existing infrastructure to enable collaborative development of machine learning model on heterogeneous environment while preserving data privacy. So I propose the LiberatAI infrastructure to remove the barrier of data usage and hardware resource for collaborative development of machine learning model. There are three main components that I propose in LiberatAI infrastructure. The first one is the model compressor. LiberatAI uses model compressor to compress the model to be fit in heterogeneous storage capacity constraint to avoid insufficient resource. Second, I propose the model aggregator. LiberatAI uses the model aggregator to aggregate the model with a diverse structure from heterogeneous computing resource for federated learning to extend the data diversity. And the third one, I propose the model specifier. LiberatAI uses the model specifier to exchange only the most updated parameters from the model on heterogeneous network to reduce the communication cost. So the last thing about my publication, since I have been a member of the Software Design and Research Laboratory, I published 2 book chapters and 3 journal articles and 12 conference papers. So thank you very much for your attention. Any questions are welcome.